Hi, good evening. Good evening, everyone. This is Celso Batalha, Astro 10, and I would like to. I don't know if you are getting and watching this tape today, but we have an exam going on. We have a midterm going on. It's the first one, and it's going to be open up to midnight. And you have a chance of retaking it on Friday. So on Friday, in fact, Thursday midnight, midterm one is open again, and then you have up to midnight Friday to complete it. So, in other words, you have two chances of getting a grade on midterm one, and you will collect the highest score when you open the second exam or the second version. Not necessarily you have the same question, so I mean, chances are you have different questions. But I would recommend you do it. It's you have better chances of improving your understanding. So far, basically, we initiated the course um, pretty much going over the basic sky motions that we are subjected to. We learn about daily or diurnal motion. We learn about the fact that Earth revolves around the sun, at the same time that rotates around its axis, and because of this yearly revolution, we experience seasons, and we also observe and see different types of constellations throughout the year as a result of Earth revolution around the sun. And there is a last or a third motion that is not so much visible or apparent. In fact, you require several generations of observations and astrometric observations, so the position of stars in respect to one another over several generations. And then you realize there are some shift, and that shift has a name. The name is precessional equinox, and that is caused by the combined gravitational pull of the sun and moon on Earth's equatorial bulge. So those are the three main motions we can observe during our night sky. And then in chapter 4, we dived into the nature of light, what light is. And chapter 4, I would say, is one of the most important chapters in this book, in the sense that provides students and provide us with techniques and with information about the only energetic representation of a faraway object we can have. So think about it. In this course, we are discussing and learning about galaxies, quasars, Big Bang, the beginning of the universe 13.7 billion years ago. We are pretty much discussing all these fantastic features and feasts, but how do we know all of that? Is this pretty much theory? Are all this information based on some factual material, or is just pretty much theory, like any other good theory, but there is no basis at all? And the answer to this question is yes. There is lots of evidence, and that evidence is brought to us first by light, and second by the instruments that capture light and bring light to the attention of astronomers, of course, computers, and then you have all the work that comes after observations have been made. So not only light, but the interaction of light with matter is very well understood by physicists and astronomers. So when we capture light, when we detect light using telescopes, in fact, astronomers, if you are not professional astronomers, people in general think that astronomy is a process by which you take picture of celestial objects. And this is pretty much far away from reality. I mean, we know about all these wonderful, wonderful things in the sky objects, about the sky objects, because we know how light interacts with matter. So the techniques astronomers use, primarily photometry and spectroscopy, are not just pictures. I mean, you can use photometry to make images. You collect photons, you collect light, and then you have an image of some region in the sky. But more than that, astronomers, they observe light, sometimes with a cadence in a consistent way, to determine if there are some changes in the brightness of the source studied. And if there are some changes, the next step is to explain how these changes might occur. Are they are they repeatable or not? Are they erratic or not? And how much change in brightness are being detected? And then astronomers pretty much value all that data, all that information that is observed. And another technique is spectroscopy. So spectroscopy is slightly different. You take the light of an object and then you spread out this light in all its basic components. And by doing so, you create a rainbow of stellar or galactic objects. And then you analyze all the different strength in the different color bands. And then you verify if there are traces, we call lines, absorptions, or emissions. And then by doing so, you can infer properties of objects being studied. So that's what astrophysicists do. Using the tools of astronomers, we can infer properties out there without the need of going to these objects. For instance, how do we know that the most populated, the most abundant element in the universe is hydrogen and helium? Well, because we observe. We observe traces of hydrogen and helium in stars. And then we also observe traces of all other elements in stars using spectroscopy, because we can identify these features down here on Earth in the laboratory. So we know exactly in the spectral range where traces of hydrogen, helium, magnesium, calcium exactly occur. And then as we observe and detect these traces in celestial objects, we can infer their presence in these objects. But not only that, depending on how strong those traces are, depending on how symmetric or asymmetric those traces are, you can then infer properties such as rotational rates, such as if the object has a companion or not, chemical abundance, temperature, magnetic activity, all kind of informations just by observing these traces. So in that sense, chapter 4 is very important. Now, chapter 5 deals with formations of stars and planets. So let's go quickly over the main points in this chapter. Let's see if I can. Okay. Oh, I lost my annotate. There you go. So stars and planets, formation of stars and planets. So chapter 5 is what are the processes guiding formations of stars and planets. So we have to be pretty much aware of gravity force, gravity, and rotation. why those two features are so important. So gravity is a force. Rotation is not a force, it's a process, it's a type of motion. But gravity is a force that has the ability of bringing objects to a point. It contracts, it brings in. Is if I let it go, this pen or this stylus, it's going to fall because the force of gravity that is produced by Earth itself is bringing this mass closer to Earth, and then it falls. So gravity is a force responsible for collecting interstellar material, pretty much gas and dust, that happen to exist in our galaxy, bring this material to a point where stars will be formed. Not only stars, but star systems. Stars, planets, satellites, and all the other components we are very well aware exist in our solar system. And what is the point of rotation? Well, when gravity takes over, material does not rain down directly to a center point, because the material itself, when gravity takes over, this material is already rotating. It has some, as astronomers call or physicists call, it has already what we call angular momentum. It has some rotational energy. And as the gravity takes over and brings this material closer to what we call center of mass, a disk, circumstellar disk, is formed around the star, and out of this circumstellar disk, planets and satellites and asteroids, comets, all of those objects will be formed. So how, contrary to the belief, I mean, if I ask questions, how stars are formed, the imaginary will dictate that there is a big explosion and the stars are formed. Contrary to that, the stars are formed by a slow process of contraction. And when stars are formed, they are primarily cooler. And as this contraction takes over, the internal temperature of stars grow. So the density, which is the ratio between the entire mass and the volume and the dimensions of the stars, increases because the dimension diminishes. The mass is the same, but the dimension diminishes. And density, so density is a quantity given by the ratio between mass and volume. So as the star contracts, the mass remains the same, but the volume shrinks, diminishes. So when you have a ratio, the denominator diminishes, the quantity that is the resulting ratio increases. So the density of the object increases, the temperature rises up, it gets hotter to the point that eventually we see it as points of light. Okay? So stars and planets forms as part of the same process. In fact, I could go even further and say that galaxies are formed kind of in the same way. So you have gravity taking over and then bringing material to a point that eventually stars initiate their process. Excuse me, and this was a long time ago. So we are going to tackle the process of star formation and apply that to our solar system itself. Can I erase all of this? Yeah. Okay, so in chapter 4, and as a result of knowing how light behaves, if you have an object that is producing radiation, is producing light, this object might radiate, might emit this light as what we call a black body. Let me show you one thing quickly here, if you allow me to. By the way, this is a great resource. There you go. Well, it's not coming. Safari is not allowing me to. See if I can do in another. Oh, I have a problem with my browser. Just a second. Let me see if I can use a different one. Sorry about that. Oh, that's Safari. Now I wanna Chrome. Just a second. Long approximation. Wait a second. Light and spectra. Light and spectra. What is it? Oh, there you go. Yeah, it's not going. Well, I have to probably update my browser. It's not allowing me to run this animation, which is too bad. But that animation is nice. So you have a metal, in fact, it's a nail. And then what you do, you just transfer energy to that nail. And initially, the nail is at room temperature. So the energy that is stored in the nail can be associated and equalize or make it proportional to the temperature of the room the nail is. But as you transfer energy to the nail, like you warm it up, you observe the temperature of the nail change, of course, because you're transferring energy. But not only that, the color of the nail also changes. So initially it appears kind of in a dark, earthy color, and then it becomes dark red. And then as you transfer more energy, that dark red becomes kind of a bright red and orange, and then go yellow. And when you get to that point, of course, the nail melts. You can't do anymore. If you could, is you transfer energy to that system, eventually you would vaporize, and you would create a plasma once the energy is so much that it can strip the electrons away from their parent atoms. So a material, an object, can radiate energy that is somehow tagged and associated to its internal temperature. We call that a black body. So a black body is an object that does not reflect light, does not, so when absorbs light, it distributed that energy in all possible wavelengths. Like I have, I'm here in a room that has a bunch of tapes with different colors. I have an orange, red, and I have a blue. I have more blue over there. I have a purple leaf. So all of those colors are not colors of a black body. They are colors that are being reflected off the surface of these objects as a result of interaction of the sunlight or the light of the light bulb with the surface material. So the surface material absorbs everything and rejects some color, and as a result we see it, that color which has been rejected. For instance, why leaves are green? Well, because the leaf itself absorbs everything but reflects and rejects the green part, and then we see it as green. So it's not a black body. If you turn off the light, the external radiation, or if you don't put the leaves in contact with the sun, you will not see it. For instance, I'm in my room. If I turn off all the lights, I can't see anything. All the red, blue, and yellow and green colors that I see around me will disappear, right? So black bodies are different. They produce light, and then you see the light with certain colors because you see, like, if you are camping and you make a fire camp, and then you see the ashes with that orange, red color, that color is a result of a material that is radiating itself. And if you are at night, you can see it as an orange color. So these black bodies, they have very specific and properties. And one of the properties is the maximum intensity, which means the maximum energy these black bodies produce is somehow associated with the color they have. For instance, red stars, they tend to produce a black body radiation that peaks like this one over here, that peaks in the red. I mean, it has all the possible colors, but the dominant color is red. And that's why stars 4,000 Kelvin are stars that appears, visually speaking, with a reddish coloration. Our sun is somewhere here. See that? So this is a curve that more likely represents our sun if we ignore all the absorptions the solar atmosphere is responsible for. And where is that curve peaking? Well, it's peaking in 5,000 Kelvin. The sun is producing a radiation in its photosphere. We are going to learn this later. Is about 6,000 Kelvin. And a star like Sirius, which is a hotter star, is peaking, which means it's producing radiation more efficiently in the blue range of the spectrum. Again, it's a hotter star. It's about 10,000 Kelvin surface temperature. So there is a relationship between temperature and color, as we see, so that the bluer the star, the hotter it is, the redder the star, the cooler it is, and that is the so-called Ian's law. Ian's law. Now, from where stars come from? So stars come from what we call molecular clouds, and there are thousands of them in our galaxy. So our galaxy still efficiently forms stars. So how do stars happen to be formed nowadays? So these giant molecular clouds, they migrate around the center of the galaxy, and they are their density is very low. It can't be compared with the clouds we have in our own atmosphere. The clouds in our atmosphere are very dense when you compare them with the clouds in the interstellar medium. So these giant molecular clouds, they interact. Sometimes they collide among themselves. Sometimes they penetrate a region in the galaxy whose density is relatively large, and which force them into compression, in a compressional mode. Sometimes these giant molecular clouds happen to be close to a star that explodes, a supernova explosion. And this explosion generates shock waves that passes through the giant molecular clouds and triggers and initiates the process of star formation. So, but giant molecular clouds, they are primarily hydrogen, as you can see over here. And if the gravity, the self-gravity of this cloud is superior, is more important, is stronger than the repulsive forces caused by pressure. I mean, any gas has pressure, because and what is pressure? Is the result of the collision the gas molecules or atoms have as a result of their internal energy, as a result of their temperature. So any gas with any temperature will be moving and colliding as a result of their internal energy. So if you increase the internal energy of a gas, more collisions will take place, which means the pressure will increase. So this pressure tends to expand the gas. But look at this, gravity tends to contract the gas. So there is a situation called hydrostatic equilibrium. Let me write this down. Hydrostatic equilibrium. So hydrostatic equilibrium exists if you have any gas, let's say a layer of gas, where the balance between the inward gravity force is balanced out by the outward pressure that is produced by gas molecules itself. So if you go to another or more external layer, then the weight of this layer is balanced out by the external pressure, right? So if you have these two conditions, the gas itself will not contract, will not expand, will stay basically the same. But if you have I think I put too many wiggly things. But if you have a different situation, and that is gravity is much more important than the repulsive forces caused by pressure itself. If this happens, the main result is your system will contract. So your system will slowly contract, and we call this contraction, or we identify this contraction as one of the most important features in a star-forming system. So you have gravity taking over and overcoming this gravitational, overcoming this gas pressure, and as a result, as collapse or contraction takes place, there will be some fragmentation that will lead to the formation of stars, as you can see right there. So that's how stars form. The stars are not formed because of exploding things. Explosions like supernova might trigger star formation in nearby molecular clouds, but the clump that you're seeing right here, so this clump right here, this is not exploding. In fact, this is contracting. So this whole system is contracting, okay? Now, contraction is not the only issue. You have another issue going on, and the other issue, and I think I mentioned in the very beginning, is rotation. So rotation is not caused by contraction itself. So rotation is there because I don't know if you have observed rivers. As the river flow, if you observe carefully, you have edgy currents, you have some rotations and some some pull or whirlpool and some rotations going on here and there as a result of viscosity and the flow of water as it interacts with the bottom of the river or rocks and things like that. And you have this small localized rotation. So these giant molecular clouds, they have their own rotation. But when contraction takes over, this rotation speeds up. So the angular velocity of the gas itself, or the Boson gas, increases to the point that eventually, if you work out your equations properly, the system itself thinks is not a good word to use, but the system prefers to collapse into a circumstellar disk that goes around the central star, and eventually you have a central star formed, like you can see in this picture, with a gap, and this gap is caused by the star itself becoming self-luminous and radiating energy and expelling gas with high temperature that causes evaporation in the dust itself near the star. And then you have star formation. So basically, when you think about star formation, especially later on when we study galaxies, you have to consider the following issue. One, when the stars are formed, eventually they will become self-luminous. Second, there will be a circumstellar disk around them. Third, since the stars get hot, this heat, this energy will shape the circumstellar material around the star itself, so that light materials, volatiles, as we say, will not be formed, like ices, will not be formed closer to the star because the star is hot. So you have a tendency of forming what we call terrestrial objects. Terrestrial objects. This word comes from terra. Terra is a Latin word for earth. So terrestrial objects. So in our solar system, terrestrial objects are, for instance, Mercury, Venus. They are all rocky type. Earth, Mars, Moon, asteroids. So they are all terrestrial objects. They are rocky type. As opposed to, in some books, they call Jovian objects or gas giants. And they are pretty much Jupiter, Saturn, Uranus, Neptune. So Neptune. So these are planets, but Pluto, all the Plutinos, all the Kuiper belt objects, they are made primarily of volatiles, of light elements, and water. So you have more of the metal oxides and rocky things closer to the sun, because the sun's heat and radiation swept out and prevent these volatiles to efficiently being formed closer to the sun. And the regions in the outskirts of our solar system, these lighter elements happen to be formed. So they have more ices over there, which seems to be intuitive, the understanding. So when planets form, they are not the same. They become different because of the proximity to the sun. Now, the circumstellar gas, this circumstellar gas is the same. I mean, the composition is the same, but it becomes differentiated as a result of the heat the sun itself produces. Like if you look at the sun, or like a planet, our Earth, Earth is also differentiated. Venus and Mercury, all these planets, they might be differentiated in the sense that once they formed, gravity and other forces rearrange the chemical mix, so that in the case of Earth, the heavy elements like iron fall and sink to the core. That's why we have an iron core surrounded by a mantle of lighter elements and an atmosphere made of volatiles. It's called differentiation. So the whole thing, if you take the whole solar system, it's primarily hydrogen, 75%, and 24 or so percent of helium, and trace amount of everything else. But once the sun forms, now the rearrangement starts. Once the planets formed, the rearrangement of the metals and Earth elements start to be rearranged and formed. Now, some stars never formed. They are called brown dwarf if they are a hundredth of a solar mass. They will be different. They will not have enough mass to provide enough pressure to the core so that fusion reactions take place. So stars are, in fact, stars, when they are mature, they have the ability of undergo fusion reactions, and hydrogen is fused into helium, and as a result, energy is produced. For instance, if the star energy source were primarily from the contraction, so as gravity takes over and the star contracts, the gas heats up, and the star becomes self-luminous, and then you can see the stars and you observe them. If contractions were the only force or action responsible for producing light, the stars would be dead in a few million years. So why they are not dead? Well, because the core, the center part of the star, gets so hot and dense that eventually nuclear reactions take place, and that nuclear reaction produces a surplus of energy that is able to keep the star shining for billions of years in the case of the sun. So the sun has 4.5 billion years so far as a result of these fusion reactions. So the stage of contraction, we call that pre-main sequence stage, takes few million years. And the stage of a star as a main sequence take billions of years in the case of sun. So we are going to study later in later chapters that mass is the main feature controlling stellar evolution. The stars that have more material, they are capable of living a longer time, and stars that have, in fact, the stars that have more material, they live shorter because they burn out energy with a faster rate. And stars that are not so much massive, it takes longer to undergo the process of contraction, take longer time to produce and convert hydrogen into helium, and as a result of them, they live longer. Examples of stars with a disk. I have some animation, and I pull up here. Let me see if I still have it. Do I have it? I think I do. That was a good one. Yes, right here. Oops, what is this? Can I clear that up? Yeah. That's a good one. Look at this animation here. This animation is based on Spitzer data, which is a space telescope that is sensitive in the infrared. And then you can see the circumstellar material rotating. Now the star gets hot, and it starts clearing the gap between the star itself and the circumstellar disk. And eventually a little planet is forming right there. You can see, you saw that. You repeat that. Did I miss that? I think that's a good animation. So usually in either an image or a simulation of a young star, you have the circumstellar disk, you have a protoplanet being formed. In the very early stages, you have what is being...
Okay, now that I got your attention, because we're changing pictures, I'd like to welcome everybody to our July open.
Not now, guy. You have these other two other features, which is the bipolar jet, which is a jet of gas that runs perpendicular to the direction of the disk. This bipolar jet is a result of conservation of angular momentum. So as the circumstellar disk contracts, so much rotational energy is transferred to the star can't handle, and this bipolar jet just come as a natural result of conservation of energy, basically. And later on, when we study galaxies, we will see similar features associated with galaxies like radiolobe, which is primarily the same idea and the same physics. And here is another young star. This black trace over here is pretty much, that you can see up in the middle of your screen, is pretty much a circumstellar disk that is so opaque that is blocking out the light of the central star, but the bipolar configuration is pretty much on view. And pretty much that's it. There you go. That's a better kind of a view of it. Okay. So again, formation of planets and stars, it runs with the same physics: gravity, rotation, and circumstellar material that is slightly, in fact, cooler than the central star. And the central star's heat is the one responsible for creating the different types of planets we have in our solar system. So closer to the star, the planets will have, you have more metal oxides than those terrestrial planets that are further out, and even further, the giant or icy planets, they will be richer in volatile and lighter elements, because they will eventually collect those. So tomorrow I will be focusing on terrestrial planets and talk more specifically about terrestrial planets. All right? Okay, good night.